6 billion kilometers from where you are, in a part of the sky no camera had ever looked back from. A machine that had been dark for 9 years was told to wake up and turn around. It needed 3 hours to warm itself through. Then, at 48 minutes past 4 in the morning, Greenwich time, on the 14th of February, 1990, it opened its shutter 3 times, 7/10 of a second, then just under half a second, then 7/10 again, and closed it. Less than 2 seconds of light altogether. 34 minutes after that, a command arrived from Earth and the cameras were switched off for good. Not paused for later, but powered down permanently, with the computer that had run them reassigned to other work. Voyager 1 has not taken a photograph since, and it never will. In one of those 3 frames, sitting inside a streak of stray light, there is a pale crescent about 12 hundredths of a pixel across. Every human being who has ever lived was born on it. Everyone you have ever loved is standing on it right now. Voyager was 40 times further from the Sun than the Earth is when it took that picture. And that is a number which is easy to say and almost impossible to feel. So here is another way into it. When the shutter opened, the light landing on it had left Earth 5 hours and 36 minutes earlier. So the photograph does not show the 14th of February at all. It shows 12 minutes past 11 on the night of the 13th, the evening before, and by the time the picture existed, the planet inside it had already turned away from the moment it recorded. The sun was standing over the Pacific at that hour. Most of what the camera caught was sunlight coming back off open water. The frame itself does not look like much. It is mostly dark, crossed by 3 or 4 broad diagonal bands of light that are not stars, and not dust, and not anything out in space at all. On one of those bands, so small that people generally have to be shown where to look, there is a single point of pale blue. We had been photographing ourselves from the outside for 44 years by then, and we had never once been very far away. The first picture of Earth from space was taken on the 24th of October, 1946, by a 35mm movie camera bolted into the nose of a captured German rocket and fired up out of the New Mexico desert. It climbed to 105 kilometers, taking 1 frame every second and a half, and then fell back and hit the ground hard enough to smash itself to pieces. The film came through only because somebody had thought to pack it in a steel case. 22 years later, on Christmas Eve, Bill Anders was in orbit around the moon when the Earth came up over its edge, and he reached for a camera without anyone having asked him to. 4 years after that, the crew of Apollo 17 caught the whole lit face of the planet from about 29,000 kilometers out. Blue and white and completely round, the one you have seen so many times that you have probably stopped seeing it. Then February 1990, and a step with no equivalent anywhere else in that sequence, from 105 kilometers to 6 billion. 58 million times further out in 44 years. Nothing has beaten it since, and only 2 other machines have ever been anywhere near the position to try. Neither of them did. Cassini turned and photographed Earth from Saturn in 2013, and Saturn is close by comparison, 1.5 billion kilometers, roughly a quarter of the way out to where Voyager was standing when it looked back. 36 years on, the most distant photograph of Earth is still the one taken by a camera that was switched off half an hour afterwards, and it is likely to hold that record for a very long time. There is something worth sitting with in the fact that we did this at all. We built a machine to leave, aimed it outward, and for 13 years it went exactly as it was told. Then, past the last planet it had been sent to look at, we asked it to turn around and find us. Not to measure anything, and not to learn anything, but simply to see whether we were visible from out there. That is an unusual thing for a species to want. Nothing else we know of has ever wondered how it looks from far away. Before we go back any further than this, one small request. In that frame, the whole planet is one smear of light. No coastlines, no cities, no weather systems, nothing that would let anyone tell one place from another. Everything folded into a single point. So say where you are inside it. Leave a comment with the place and the time it is there. The real time, whether that is the middle of an afternoon or 3 in the morning with the lights already off. They all get read. There is something about seeing them gathered together that comes closer to what this photograph means than any sentence about it could. And if this is the kind of night worth having again, slow, unhurried, with something large in it, the subscribe button is there. No urgency about it. The photograph is 36 years old now, and it has been reproduced so many times that it has stopped looking like a photograph and started looking like an idea. It hangs on classroom walls, and it gets read aloud at funerals. Almost none of that was supposed to happen because for 8 years the answer was no. It was not an unreasonable no either. The people refusing were protecting a working instrument on a mission that had already cost $865 million, and the thing they were being asked to risk it for had no scientific value at all. The picture would measure nothing, settle nothing, and answer no question that anyone had thought to ask. It would only show us where we live. That was the whole of the argument, and it ran for the better part of a decade before anybody won it. Strip away everything that has been said about the photograph since, and what he was actually asking for was that somebody point a telescope at the sun. Carl Sagan was not lobbying the space agency from the outside. He was a member of the Voyager imaging team, one of the people whose job it was to decide where the cameras looked and for how long. So when he made the proposal in 1981, the year after Voyager 1 came past Saturn, he was making it to his own colleagues. They turned him down. The difficulty was never that the request was eccentric. It was geometric, and it could not be argued with. From out where the spacecraft was heading, Earth does not sit off in some safe quarter of the sky where a camera can be aimed at it in peace. It sits almost on top of the sun. At 40 times our own distance, the angle between the two comes to about 1.5 degrees, and the narrow-angle camera saw 4/10 of a degree at a time. The sun would be just outside the frame, 3 or 4 camera widths away, no more than that, pouring light past the edges of the picture the whole time the shutter was open. Aim a slow-scan television tube that close to the sun and the light-sensitive surface inside it can be burned. This is not the same as ruining a single exposure and trying again. The damage would be to the detector itself, permanent, and a very long way past the reach of anybody who might have repaired it. Set against that was a photograph everyone involved already knew would show nothing. Nobody was promising a discovery. From that range, Earth would come out smaller than a single picture element, and this was calculated in advance rather than discovered afterwards, so the frame would carry no detail of any kind whatsoever. Sagan was not asking his colleagues to gamble a working instrument on the chance of learning something. He was asking them to gamble it on an image that was designed to be almost empty. He was not alone in wanting it either, and that matters, because it means the idea never depended on one man's temperament. In 1983, Carolyn Porco arrived at the same proposal independently, and within 2 years she was putting it forward through formal channels of her own. The requests went in and came back declined. 6 of them by the space agency's own count, or 7 if you count them the way Porco does, and either way, the figure that matters is the other one. 8 years of asking. The refusals were not all about the sun either. The Voyager team through those years was small and getting smaller, and almost every hour of sequencing work it had was committed to Voyager 2, which was still out in the middle of the tour. Uranus arrived in January 1986, Neptune in August 1989. Building a command sequence for a spacecraft is nothing like pointing a camera and pressing a button. Every instruction has to be written, checked, simulated, and then uploaded across a delay measured in hours. and the people capable of doing that work were doing it for planets no one had ever seen up close. What eventually broke the deadlock was not a change of anybody's mind. On the 25th of August 1989, Voyager 2 passed Neptune, and the tour was over. There were no further planets in front of either spacecraft, no more close encounters to keep the cameras safe, or nothing left ahead that any of it needed to be protected against. The instrument that had been too valuable to risk had, in the space of a single week, almost nothing left to be valuable for. Somebody still had to decide to actually do it, and that decision came from the top of the agency. Richard Truly, then its administrator, backed the observation, and then went on backing it, because approval turned out to be only the first obstacle. Staff were rotating off the project. Instruments wanted recalibrating. A piece of work with no scientific return and no deadline attached to it is the easiest thing in the world to let quietly slide, and this one was not allowed to. The job itself went to two people, Candy Hansen at the Jet Propulsion Laboratory in Pasadena, and Carolyn Porco, who by then had been asking for it for 6 years, were handed the task of building the command sequence and working out the exposures, how long to hold each shutter open on a target nobody had ever photographed from anywhere near that distance, using a camera that had been switched off and cold for the better part of a decade. Laid out plainly, the arithmetic of those 8 years is a strange thing to look at. 6 or 7 formal requests, meetings, memoranda, calculations, and refusals that were correct every time they were issued, and what the whole of it purchased in the end was under 2 seconds of open shutter. It is easy now, with the picture already hanging on the wall, to be certain which side of that you would have taken. It becomes a good deal harder if you are standing in the room in 1985 with the numbers on the table. A functioning instrument on one side of the ledger, and on the other an image guaranteed to contain nothing, asked for by a colleague who could not say what it was for in any language a review board was equipped to accept. For 8 years, the question on the table was whether a working camera was worth spending on a single look back at the place every one of them had been standing when they built it. And the people who kept saying no were not being timid, and they were not being small. They were protecting an object that could not be replaced and could not be repaired, sitting cold in the dark somewhere out beyond Saturn, and which was not in any way that would be familiar a camera at all. At the center of it, there was a glass tube about 25 millimeters across, roughly the width of a wine cork, and the whole of the argument came down to what had been painted on the inside of one end. That coating was photoconductive, which means it did something slightly unusual with light. It did not generate a current when light struck it. It changed how well it carried one. Kept in the dark, the surface held its charge evenly across the whole of its face. Wherever light landed, the charge leaked away in proportion to how much had arrived. Open the shutter on a scene, and what forms on the inside of that tube is nothing a person could look at. It is a map of electrical charge, full where the scene was dark, drained where the scene was bright. Getting the map back out again took an electron gun. At the far end of the tube, a filament threw a narrow beam forward, and magnetic coils wound around the outside steered that beam across the charged surface line by line, the way a reader crosses a page. Wherever the beam touched down, it topped the charge back up, and the amount of current required to do that at each individual point was the measure of how much light had fallen there. That current coming off the tube in sequence was the photograph. The reading and the erasing were the same motion. The beam could only measure the charge by restoring it, so every line it read, it wiped as it went, which means each image existed exactly once on glass and was consumed in the act of being taken off it. It did this slowly, and the slowness was the point. A television camera in 1977 was pulling 25 or 30 complete frames off its tube every second, because that is what moving pictures demand. Voyager's cameras had no interest in movement. They were built to hold still and read a single frame with care, and that reading was measured in tens of seconds rather than fractions of one. The whole apparatus was closer in principle to the back of a television set in 1965 than to anything you have ever held in your hand. And it is here that the 8 years of refusals stop being a matter of temperament. A vidicon stores an image as charge and gives it up when the beam comes past. Flood it with far too much light and it stops giving it up cleanly. Whatever was bright enough remains in the surface, faintly at first, then less faintly, and reappears in the following frame, and the one after that worked into the photoconductor like a stain in cloth. Aim a tube like that at the sun, and what stands to be lost is not one ruined exposure, but the instrument itself, left with the sun printed into it, surfacing in every picture it takes for the remainder of its life. Around the tube sat a telescope, 1,500 millimeters of focal length, with the light path folded back on itself between a mirror and a set of correcting lenses so that all of it fitted into a far shorter body and an aperture of 176 millimeters. An instrument, in other words, of roughly the size and the reach that a committed amateur astronomer might keep in a shed at the end of the garden. What it took in at any one moment was a patch of sky slightly smaller than the full moon. In front of it, on a wheel that could be turned by command from Earth, sat 8 filters. The camera could not see color at all. It could only measure brightness, one filter at a time, so a color photograph meant 3 separate exposures through 3 separate filters, taken one after another, stored and stacked back together by people on the ground. No single frame Voyager ever took was a color image. Every color picture that came from it was assembled afterwards. Each frame arrived as 800 lines of 800 points, every point carrying a brightness value somewhere between 0 and 255. That was the entire resolution of the thing. None of it was new when it launched either. The design came down directly from the cameras carried on the Mariner probes of the 1960s, the ones that sent home the first close photographs of Mars, and by 1977 it was already mature, thoroughly understood and mildly old-fashioned. By 1990 it had been an old design for a quarter of a century. The spacecraft it was bolted to weighed a little over 700 kilograms dry, about as much as a small car, and the thing anyone would notice first was the dish, 3.7 meters across, the width of a modest bedroom, aimed permanently back the way it had come. 470 watts at launch ran all of it. The instruments, the heaters, the radio, the computers, everything. And spread across 6 separate computers, there was room for something like 68 kilobytes of memory. A single photograph from the phone in your pocket would not fit inside it. It would overflow the entire memory of the spacecraft several dozen times over. 12 days after leaving, that camera had turned once and caught the Earth and the Moon together in one frame from 11.5 million kilometers out. The first time anybody had managed to get both into a single shot. Then it faced forward, and for 13 years it did not look back. So that was the object at the heart of the argument. A coated disc of glass behind an amateur's telescope, riding on a machine the size of a car that thought with less memory than a snapshot. Irreplaceable because nobody was ever going out there to fix it. And by February 1990, it had been switched off and cold for 9 years, aimed at nothing in particular, sitting in a part of the sky that no spacecraft had ever been built to occupy. It got there because of a moon. Voyager 1 left Cape Canaveral on the 5th of September 1977 on top of a Titan Centaur, 16 days after its twin, and on a faster, steeper path that would let it overtake the other spacecraft long before either of them reached Jupiter. The numbering has been confusing people ever since. Voyager 2 went first and arrived second. Jupiter came on the 5th of March 1979. The spacecraft passed within 349,000 kilometers of the cloud tops, which is closer to Jupiter than the Moon is to us, and it came out the other side moving considerably faster than it had gone in. Nothing had pushed it. What it had done was borrow a share of the planet's own motion around the Sun, swinging in behind Jupiter and letting the gravity of the thing drag it forward. And Jupiter paid for that speed out of its own orbit in an exchange so lopsided, given that the planet outweighs a Voyager by more than 1,000,000,000,000,000 times, that the cost will never be measurable by any instrument that could be built. 4 days after the closest approach, an engineer at the Jet Propulsion Laboratory named Linda Morabito sat down to a piece of entirely routine work. The way a spacecraft is located in deep space, where there is nothing nearby to measure against, is by photographing something whose position is already known. A moon, generally, against the fixed background of stars behind it, and then working the geometry backwards. The moon in these particular frames was Io. Nobody was looking at Io, they were looking past it, at the stars, to find out where Voyager was. The stars came out faint, so Morabito stretched the contrast of the image to lift them clear of the background, and something else came up with them. Standing off the edge of Io, out over the black, was a shape that had no business being there. A wide, thin dome of material, umbrella-shaped, rising about 270 kilometers above the surface and catching the sunlight along its upper edge. Io is a moon roughly the size of our own, and it was throwing material a quarter of the way to orbit. Nothing beyond the Earth had ever been seen doing anything of the kind. When the team went back through the frames the spacecraft had already sent and looked at them properly, they found 7 more, 8 active volcanoes in the very first set of photographs anyone had taken of the place. The one that had come up out of the contrast stretch was eventually given the name Pele. Jupiter's gravity had thrown Voyager 1 on towards Saturn, and Saturn was where the decision waited. On the 12th of November, 1980, the spacecraft passed within 6,490 kilometers of Titan, and then, later the same day, came within about 124,000 kilometers of Saturn itself. The order matters, because the Titan pass was the whole reason for the shape of the encounter. Titan is the only moon in the solar system wrapped in a serious atmosphere, mostly nitrogen, with a pressure at the surface about half again what it is in the room you're in. And the trajectory had been laid out years earlier so that the spacecraft would slip behind it as seen from Earth, letting its radio signal cut down through that atmosphere on the way home, and give up the structure of it layer by layer. It worked. It also could not be undone. Coming away from Saturn, Voyager 1 had been bent upward and out of the flat plane in which the planets travel, climbing at nearly 35 degrees to it and still rising. There was nothing in front of it anymore. No further world could be reached from that angle by any maneuver it carried fuel for, and its planetary mission, the thing it had been built and launched and paid for, was finished the moment it cleared Saturn's rings. Its twin, still traveling in the plane, was the one that went on to Uranus and then to Neptune. So the price of a few hours alongside Titan was 2 planets, the only 2 worlds in the solar system that no spacecraft had ever gone near. That is the trade as it looked at the time, and on those terms it was a reasonable one. What nobody was weighing, because nobody had any reason to, was what the angle itself would turn out to be worth. The solar system is very nearly flat. Set a dinner plate on a table and put a crumb on it for each planet. Then lower your eye until it is level with the rim, and every crumb collapses onto a single line, one behind another, with the middle of the plate hidden somewhere among them. That is the view from inside the plane. Everything is strung out along one narrow band of sky. Everything is close in angle to the sun, and the glare of it swallows whatever it does not simply hide. Lift your head 30 degrees, and the plate opens into a circle, and the crumbs come apart, and each one stands at its own distance from the center with clear black between them. every human being who has ever lived has looked out at the sky from a crumb near the middle of that plate, at eye level with everything on it. Voyager 1, in February 1990, was the only object we had ever made that was standing up. Nobody had put it there for that. The angle was a leftover, the unwanted change from a transaction made for the sake of one moon with an atmosphere, and it had cost 2 planets to acquire. What it bought was the single position in the solar system from which every world we have, including this one, could be caught separately in one sweep by one camera. The camera was on board. It had been dark since Saturn, and it would stay dark through every year of the asking. The instruction that finally woke it had to be written months in advance, and once it left Earth, there was nothing anybody could do to change any part of it. At that distance, a question asked of the spacecraft and answered by it took a little over 11 hours to complete the circuit. So the whole observation, every pointing, every filter, every shutter time in order, had to be composed on the ground, checked, simulated, converted into machine instructions, and sent out to sit in the spacecraft's memory until the appointed moment. There is no version of this in which somebody watches the first frame come in, decides it is wrong and adjusts. By the time you saw the first frame, all 60 had been taken and the cameras had been switched off for hours, which meant the exposures had to be right on paper. Candy Hansen and Carolyn Porco were working out shutter times for a set of targets that had never been photographed from anywhere near that far away, using a camera nobody had operated since 1981. The brightness range across the sequence was enormous. Venus, close in and wrapped in white cloud, throws back a great deal of light. Neptune, 30 times further from the Sun than we are, and photographed from further still, is faint almost past the point of usefulness. Every planet needed its own calculation, and every calculation had exactly one attempt in it, because when it was finished, the cameras were going to be turned off. They also deliberately photographed the Sun. After 8 years in which the single serious objection had been the danger of pointing a vidicon anywhere near it, the sequence included a frame of the Sun itself, taken through the darkest filter the wheel carried and with the shortest exposure the shutter could manage. From out there, the Sun is a small thing, a disk rather than a blaze, giving something like a 1600th of the light it gives here. It was still, by an enormous margin, the brightest object in that sky. The cameras came on during the 13th of February and needed 3 hours to warm through. A 9-year cold instrument in vacuum does not simply switch on and start working. And then the sequence began to run. It ran as a sweep. The wide-angle camera worked across a broad arc of sky in plain grayscale, 39 frames of it, laying down a strip that would later show where everything sat in relation to everything else. Into that strip, the narrow-angle camera dropped its own contributions, 21 frames, 3 apiece through coloured filters, aimed one at a time at individual worlds. 60 frames in all. Attempts were made on 7 of the 9 planets. 6 of them came back. Mercury was never really in play. It sits so close in that the glare swallows it, and pointing at Mercury from out there means pointing at the Sun. Pluto, still, in 1990, the 9th planet, was too small and too far and too dim to register at all. Mars is the one that stings. Mars was attempted. From Voyager's angle, it was showing only a thin crescent, and the coloured filters, which take a bite out of the light every time they are used, took more than the crescent could spare. A clear filter would very likely have caught it. By the time anybody on the ground understood that, the sequence was running 6 billion kilometres away with a set of instructions that could not be recalled, and the moment had gone. Earth's turn came at 48 minutes past 4 on the morning of the 14th. 3 frames, one after another, through the blue filter, then the green, then the violet. The green one held open for the shortest time of the 3, because the target sat in a difficult place and the calculation said so. It was Valentine's Day, if that helps to fix it. Wherever you happened to be that morning, or whether you were anywhere at all yet, nobody in the room with you knew that any of this was going on. 34 minutes later, at 22 minutes past 5, the cameras were shut down. The computer that had been running them was reassigned to other work, and the imaging science subsystem, 2 tubes, 16 filters, and a pair of telescopes that had brought back Jupiter, the volcanoes of Io, the rings and the haze over Titan, was finished. Voyager 2's cameras had already gone dark after Neptune. Those 60 frames are the last photographs either spacecraft has ever taken, and the last either of them ever will. And for 5.5 hours afterwards, nobody knew. That is simply how long it takes for anything to get here from out there. The shutter had closed, the cameras were cold, and the most reproduced photograph of this planet had already been taken and written onto a spool of magnetic tape. And there was not one person anywhere on Earth aware that it existed. The confirmation was still crossing. When it finally arrived, and somebody could say out loud that the thing was done, it was getting on for 11 in the morning, Greenwich time, and the cameras had been dead since before dawn. 5.5 hours is also near enough how long the light in those 3 frames had been travelling before it got there. Whatever was caught in them had left this planet the previous evening and crossed 6 billion kilometres of empty space to arrive. And it had not started here either. It began at the Sun, 8 minutes and 20 seconds before it reached us. That is the crossing time for light between there and here, and it has been the same crossing time for every photon that has ever arrived. The sunlight on the back of your hand left its source before anyone had thought about going outside. What arrives is a broad spread of wavelengths, most of it in the part of the spectrum our eyes happen to work in, and it comes down onto the top of the atmosphere at a little over 1300 watts for every square meter facing the right way. About 70% of it stays. It goes into warming the oceans, into evaporating water, into the slow churn of weather, into the leaves of things that are trying to grow. The other 30% is thrown straight back out again, off the sea, off the ice, off the deserts, off the top of every cloud, off anybody standing outside in it. That figure, 30%, is what makes this planet visible from anywhere at all. Without it, there would be nothing to photograph. And on the way back out, it changes colour. The blue you see when you look up is not the colour of anything. It is the colour of a process. Air molecules are far smaller than the wavelength of visible light, and something that's small does not reflect light so much as it takes it in and throws it out again in every direction, and it does that far more energetically at the short end of the spectrum than the long. Blue and violet get scattered several times more strongly than red does, which is why the sky overhead is blue and why the sun goes orange when its light has to come in through a longer slant of atmosphere at the end of the day. That scattered light does not only go sideways into an eye at ground level, it also goes up. Underneath it, the oceans are doing something related but distinct. Water absorbs red and near-infrared light greedily within the first few meters and lets the blue penetrate and scatter back. So the 2 largest features of the planet, an atmosphere and a great deal of water, are both, by different mechanisms, sending blue upward and holding on to red. What stops it from being a deep blue is the weather. Clouds are white. They reflect the whole visible range more or less evenly, which means every cloud in the frame is diluting the blue with something closer to plain sunlight, and there is a great deal of cloud. Take the clouds away entirely and leave nothing but ocean, and the planet's reflectivity drops from 30% to about 11%. It would be a far deeper blue and a far darker object, and considerably harder to find. Most of what made Earth bright enough to register at 6 billion kilometers was the weather passing over it. Light leaving a planet does not travel as a beam. It leaves in every direction at once, spreading over the surface of a sphere that grows as it goes, thinning by the square of the distance the whole way. By the time that sphere had swelled to 6 billion kilometers, the share of it falling into a circle of glass not quite 20 centimeters across was a quantity there is no comfortable way to write down. Everything else went past and is still going. There is also a limit from out there to how much of the planet can be lit at all. Earth never wanders more than about 1.5 degrees from the Sun in Voyager's sky, because the whole of our orbit, seen from that distance, fits inside a circle less than 3 degrees wide. A fully illuminated Earth does exist from that vantage point, but only when the planet has swung round to the far side of the Sun, at which moment it is directly behind the Sun and cannot be photographed by anything. So a fully lit Earth is not something you can wait for out there. The best available view of a day-lit Earth, for anyone in a position to see it at all, is about half of one. Which brings the arithmetic down to something small enough to hold. Take the full moon as it hangs over a garden, 0.5 degree of sky, near enough. 1,000th of that width is roughly what one picture element on the narrow-angle camera covered, the whole of its view being a little under a moon across and cut into 800 points. Against that scale, the entire Earth, dayside and nightside together, spans about 1/4 of a single one of those points. Only the daylight portion registered. Measured across, that lit sliver comes to about 12 hundredths of one picture element. And the mark in the photograph is plainly larger than that, which it has to be. No optical system hands over a point of light as a point. A lens takes anything small and bright and smears it across its neighbours, and the smaller the source, the more of the result is the smearing rather than the thing itself. The blue mark in that frame is several picture elements wide, and almost none of that width is the planet. What has been recorded there is mostly the instrument's own response to something it could not resolve. The shape an eye makes when it meets a thing it cannot quite see. Print the whole frame 1 meter across, and the daylit Earth in it comes out as a mark about 1/7 of a millimeter wide. Hold a hair up against the light and you have it, near enough, and it is not the strangest thing in that picture. What almost everybody notices first, and what nearly every description of this photograph reaches for, is that the Earth appears to be hanging inside a beam of light as though something were shining on it on purpose. That beam is a fault in the camera. The narrow-angle camera looked out through 5 optical elements, with a further lens sitting between the shutter and the face of the tube, and a mirror folding the light path back on itself somewhere in the middle. Every one of those pieces of glass has 2 surfaces. Every surface, however finely made and however carefully coated, sends some small fraction of whatever passes through it back the other way. In ordinary use, this is of no consequence. The stray fraction is minute. Most of it scatters harmlessly into the blackened walls of the barrel and the sunshade at the front. A plain tube, whose only job is to keep light from outside the field of view from getting in, handles the rest. A sunshade, though, works on angles. Point the camera well away from the sun and it does exactly what it was built to do. Point it 1.5 degrees away, which is as far from the sun as the Earth ever gets from out there, and the shade is being asked to exclude something that is effectively standing in front of it. Sunlight came straight down the barrel, met the glass at a shallow angle, and did what light does under those conditions. Most of it carried on, and a little of it turned around. What arrives at the detector, after all, that is not a picture of anything. It is light that has lost its way inside a machine and landed on the target regardless, spread across the frame in broad diagonal bands whose shape and position are set entirely by the internal geometry of the instrument, by where the elements sit, how they are mounted, and where the sun happened to be with respect to the axis of the tube. It is the same defect that has spoiled photographs you have taken yourself. The smear of light across a picture shot towards a window, the pale streak that appears when the low sun is just outside the edge of the frame. In terrestrial photography, it is a nuisance, and people buy lens hoods to prevent it. None of it came as a surprise either. Anybody who had worked with those cameras knew what pointing that close to the sun would do to a frame, and there was no arrangement of the spacecraft, no angle, and no timing that could have avoided it. Earth cannot be photographed from the outer solar system without the sun being in roughly the same direction. There was never a version of this observation without the streaks in it. And the position of those streaks has nothing whatsoever to do with the position of anything in the sky. They are a property of the instrument, fixed by glass and mounting brackets. Where Earth fell in that frame was a property of where Earth was, fixed by orbital mechanics. The two were determined by entirely separate things, and there is no mechanism by which either could have influenced the other. The planet landing inside one of the bands was luck. There is a second thing in that frame that is not quite what it looks like, and it has to do with the color. 3 exposures were made: blue, then green, then violet. And when the picture was finally assembled on the ground, the green measurement was put into the red channel, the blue into the green, and the violet into the blue. So what reads as blue on your screen is violet filter data, and what reads as red is green. No part of the most reproduced color photograph of this planet was taken through a red filter, for the straightforward reason that nothing in the sequence was looking at red. The blue itself is not an invention. Earth genuinely does throw back a great deal more short-wavelength light than long, which is precisely what those 3 exposures measured, so a bluish result is the honest one. But the particular color is a translation, real measurements, made through filters that bear no relation to the human eye, shifted into the 3 channels a screen is capable of showing. In 2020, 30 years afterwards, the frames were worked through again. Kevin Gill, an engineer at the Jet Propulsion Laboratory, went back to the original data alongside Candy Hansen, who had helped calculate the exposures in the first place, and William Kosman, another of the original planners. They lifted the brightness, cleared out a good deal of the grain, and rebalanced the 3 channels against one another so that the main streak, the one the Earth is sitting in, came out white. That was a deliberate correction rather than a decoration. The streak is scattered sunlight, and sunlight is white, and in the 1990 assembly it had picked up a tint that belonged to the filter set rather than to the light. The released frame runs a little under 700 pixels on a side, and it is almost certainly the version you have in your head. It is also 30 years younger than the photograph. In February 1990, none of it had been seen by anyone. There was no image to look at, no streak to remark on, no pale mark that visitors had to be shown how to find. What existed was a set of magnetic patterns written onto a loop of tape aboard a spacecraft that had just finished switching off its own eyes, 6 billion kilometers from the nearest person who could have done anything at all with them. The tape existed because the spacecraft could not hold a photograph. One frame off that camera came to 800 lines of 800 points, with 8 bits of brightness at every point, which multiplies out to 5,120,000 bits, around 640 kilobytes in the units we use now. The entire computer memory of Voyager spread across all 6 of its machines came to 68. The thing could not have held a single one of its own pictures in its head. Each frame was very nearly 10 times too large. So there was a tape recorder aboard, and everything the cameras produced went onto it first. It held 536 million bits and wrote at 115,200 bits a second, which put a frame down in about 3/4 of a minute. Divide one of those figures into the other, and the whole photographic memory of the spacecraft, everything it was capable of holding at once, anywhere, comes to something in the region of 104 images. The 60 frames taken that February had filled rather more than half of it. Getting any of it home was the slow part. The transmitter aboard Voyager runs on about 23 watts, less than the bulb inside a refrigerator, and considerably less than the lamp in whatever room this is being listened to in. That is the entire broadcasting power of the most distant object our species has ever built, and it has never had any more than that. At 6 billion kilometers, the rate that little transmitter could sustain was 8,400 bits a second, or 14,400 when conditions allowed, which put a single frame somewhere between 6 and 10 minutes on the air. All 60 of them, back to back with no gaps at all, would have taken about 6 hours of continuous transmission. 14,400 bits a second was, at the time, roughly what the fastest telephone modems could manage. If you are old enough to have owned one, you know the noise they made. That sequence of tones and hiss while two machines negotiated how to talk to each other, and then the long patient wait while an image assembled itself downward across the screen, a few lines at a time. That is the speed at which the most reproduced photograph of this planet came home. The phone you are holding moves more data in a single second than Voyager could send in an hour. At the receiving end, the arrangement is the reverse of the spacecraft in every respect. Voyager transmits with 23 watts through a dish you could fit inside a bedroom. What listens for it is the Deep Space Network, and there are 3 of them, and there have only ever been 3. One at Goldstone in the Mojave Desert of California, one outside Madrid, one outside Canberra. They sit roughly a third of the way around the world from each other, which is deliberate, as the Earth turns, and it turns whether or not a spacecraft is talking. At least one of them always has the sky in question above its horizon. Everything we have ever sent into deep space speaks through those 3 sites. The dishes that caught this particular signal had been enlarged the year before, and not for this. Their main antennas had stood at 64 meters across for years, and Neptune was going to be too faint for that, so all 3 were rebuilt out to 70. Goldstone finished in May of 1988, Madrid in July, Canberra in October, in time for Voyager 2's encounter the following August. The metal that received the pale blue dot was there because of a planet in the opposite direction. What arrives at those dishes is almost nothing at all. The power collected from Voyager is measured in units most people never have cause to use. A watt divided by 1,000 million, and then divided by 1,000 million again. That is the scale of it. The signal was stronger in 1990, when the spacecraft was a quarter of its present distance, but only by a factor of 10 or 20, which is to say it was still nothing. 23 watts leaves the antenna. Something in the order of 20 billion times less than that is what reaches the desert. Everything else spread outward into the dark and went past us, and is going still. Pulling a whisper like that out of the noise takes receivers chilled to within a few degrees of absolute zero, so that the electronics themselves are not humming loudly enough to drown it, and it takes knowing precisely where to point and precisely what frequency to expect. The signal is not louder than the background. It is simply the only thing down there that is saying anything in a pattern. And it came home in pieces. The frames were played off the tape and sent across several separate passes, beginning in March and running on into the spring. Because the Deep Space Network belongs to every mission at once, and Voyager, with no encounter ahead of it and nothing urgent to report, took whatever time it could be given between other people's appointments. 6 hours of actual transmission, spread across the better part of 2 months. The last of the image data came down on the 1st of May 1990. Somewhere in that slow trickle, arriving between other work, was a frame that nobody had yet had reason to look at closely. The person who found it was Candy Hansen, who had spent part of the previous year working out how long to hold that shutter open. Finding it was not a simple matter. The frames came down over a period of weeks and had to be gone through one at a time. and the object in question occupies 12 hundredths of a picture element in an image made of 640,000 of them. It sits inside a bright, diagonal band of scattered light, which is precisely where a small pale smudge is what the camera's own faults would be expected to produce anyway. Everyone who has looked at that photograph since has been shown where to look. She had nobody to show her. The wide-angle frames went to the multi-mission image processing laboratory to be fitted together. 60 separate exposures resolved into a single long band of sky with 6 planets in it, each one a point, each point at its own distance out from the center, and no two of them the same brightness. The last of the data came down on the 1st of May. 5 weeks after that, the pictures were shown to the world. On the 6th of June, 1990, a news conference was held in Washington. It ran for an hour and a half, which is a considerable length of time for a press event about a set of photographs in which almost nothing is visible, and it had been called to mark an ending, the close of Voyager's planetary mission, 13 years after launch, and the formal beginning of whatever came afterwards. 2 people hosted it: Ed Stone, the project scientist for Voyager, and Carl Sagan. Almost everybody who knows what was said in that room believes it came from the book. It did not. The book was 4 years away and had not been written. What happened on the 6th of June, 1990, was that the photograph was put in front of the press for the first time, and the man who had spent 9 years asking for it stood up and said what he thought it was, and gave it the name it has carried ever since. "This is where we live," he said, "on a blue dot." You have almost certainly heard some version of that. Very few of the people who have heard it know that it was first spoken in early June of 1990 at a press conference about the end of a mission, with the frame itself standing on a board behind him and 5 other planets in the same set of pictures that nobody remembers at all. What is less often quoted is where he took it. The passage is usually remembered as being about how small we are, and about half of it is, but he did not finish on the smallness. What he asked for at the end was that we preserve and cherish that blue dot, the only home, he said, that we have. The famous part is an observation. The part that follows it is an instruction, and he meant it as one. The name took hold at once and completely. 9 years of asking had gone into opening that shutter. It took 16 weeks from the moment it closed for the picture to acquire the name it still answers to, and in the 36 years since, through reprocessing, through reprinting, through more reproductions than anyone has counted, nobody has ever managed to call it anything else. That is genuinely unusual. Most famous photographs accumulate titles, or get known by their subject, or end up filed under a catalogue number. This one has had a single name from its first public day, given to it by the person who had argued longest to have it exist. The book followed in 1994, published by Random House, taking both its title and its opening from what had been said in that room. Sagan read the audiobook himself, and it is that recording, his own voice, unhurried, working through his own sentences, that most people have actually encountered. If you have heard the passage rather than read it, that is almost certainly the version you heard. In 2023, the Library of Congress entered the recording into the National Recording Registry, the archive the United States maintains for the recordings it has decided to keep permanently. Carl Sagan died on the 20th of December, 1996, 6 years after the press conference, 2 years after the book, and 30 years before the photograph reached the age it is now. What that image did to people was not, in itself, without precedent. Photographs of this planet taken from somewhere outside it have been quietly rearranging how we understand the place for as long as there have been cameras capable of leaving it. This one was the furthest away, and the smallest, and the last. It was also the fourth. The first of them was taken from a weapon, and it is worth being specific about what kind. The V2 was the first object built by human beings to reach space, and it was built to arrive somewhere and explode. Several thousand of them were fired at London and Antwerp in the last year of the war, arriving faster than sound. When Germany surrendered, the United States shipped the surviving rockets and a good many of the people who had built them across the Atlantic, and by the autumn of 1946, there were V2s standing on test stands in the New Mexico desert with scientific instruments bolted in where the warhead used to sit. The camera was one of those instruments. The flight that carried it was designated V2 number 13. It went straight up and it came straight back down, and it struck the desert at something like 550 kilometers an hour with the camera still inside it. The camera did not survive that. The film, wound into a steel cassette, did. And they kept going. Between 1946 and 1950, cameras flown on captured rockets out of White Sands brought back more than 1,000 photographs of the Earth from above the atmosphere. None of it was sentimental. Those flights were the start of serious atmospheric research from altitude, and the pictures were data. For 22 years afterwards, everything anyone knew about how this planet looks from outside came from machines. Nobody had been out there to check. Then, in December of 1968, 3 men were sent around the moon. Frank Borman, Jim Lovell, and Bill Anders were the first human beings to leave the Earth's immediate gravitational neighborhood altogether, and therefore the first to be far enough away to see the whole of it at once. On Christmas Eve, on the 4th of 10 orbits, 110 kilometers above the lunar surface, the spacecraft rolled and the Earth came up over the edge of the moon. The planet was about 380,000 kilometers away in that frame, which is worth holding on to, because the photograph that replaced it in the public imagination 4 years later was taken from 13 times closer. On the 7th of December, 1972, on the outward leg, the crew of Apollo 17 caught the planet from around 29,000 kilometers with the whole disk lit from edge to edge. It is credited officially to the crew, since nobody is entirely certain which of the 3 pressed the shutter, though it is usually attributed to Harrison Schmitt. What made that photograph possible is precisely the geometry that made Voyager's impossible. To see a planet fully lit, the sun has to be behind you. Apollo 17 was running outward with the sun at its back, so the face turned towards the camera was the daylight face, entire. Voyager, approaching the problem from the far outside with the sun beyond its target, could never have obtained that view from any position it was physically able to occupy. One planet, photographed twice, 18 years apart, from opposite sides of the light. Apollo 17 was also the last time anybody left low Earth orbit. In the 54 years since, nobody has been far enough out to take that picture again. What being out there does to the people who go has a name, and the name was not supplied by any of them. Frank White was a writer with a background in philosophy, and he had noticed something on aeroplanes. Sitting at 30,000 feet, the altitude you have been at yourself on any long flight, with the cloud deck below and the horizon just beginning to bend. He found that his thinking about the ground down there changed in a way that felt structural rather than merely moving. Borders stopped being convincing. The place became difficult to think of as anything other than one object. He went looking for the same thing in people who had gone considerably further and found it described over and over in the accounts of Apollo, Skylab, and shuttle crews. In 1987, he published a book arguing that the shift was consistent enough from person to deserve a technical term, and he called it the overview effect. The reported features are remarkably uniform for something so interior. The planet is perceived as a single living system rather than a collection of separate places. Attachment to nationality weakens, sometimes abruptly. Almost everyone remarks on the atmosphere, not its beauty but its thinness, how little of it there is, how visibly finite that blue band looks when seen edge-on from above. And it does not wear off. People describe it as still running years after they came home. Edgar Mitchell, coming back from the moon aboard Apollo 14 in February 1971 after walking on it, spent much of the return journey watching the Earth turn in the window and spent much of the rest of his life trying to give an account of what had happened to him while he did. Rusty Schweickart, on Apollo 9, ended up with a few unscheduled minutes outside the spacecraft in Earth orbit and nothing to do in them, and spent decades afterwards attempting to describe those minutes to people who had not had them. None of this is treated as anecdote any longer. The Canadian Space Agency includes material on the overview effect in the psychological preparation it gives its astronauts, on the working assumption that anyone who goes up is likely to come back altered and had better be told so beforehand. The number of people who have actually seen it, though, is smaller than almost anyone assumes. 24 human beings have ever been far enough from this planet to take in the whole of it at once, with their own eyes, through a window. All 24 went between December 1968 and December 1972, 9 flights inside 4 years. 3 of them made the journey twice, which is why the figure is 24 rather than 27. Nobody has done it since, and nobody now living is certain to do it again. Everyone else who has ever lived, including you, has only ever seen a photograph of it, so we went on making them. And the next one, taken from beside another world, came with an appointment. On the 19th of July, 2013, at an hour that had been announced weeks in advance, a considerable number of people went outdoors and looked up in the general direction of Saturn. You may well have been one of them. What they were looking towards was a spacecraft called Cassini, which had been in orbit around that planet for 9 years and was at that moment sitting inside its shadow. The shadow was the whole point. Photographing Earth from Saturn runs into the same difficulty that had held Voyager up for the better part of a decade. From out there, this planet never strays more than about 6 degrees from the Sun, so aiming a camera at it means aiming very nearly at the thing most likely to ruin the camera. Voyager had no way around that and simply accepted the damage to the frames. Cassini had an option Voyager never did. It could wait until Saturn itself passed between the spacecraft and the Sun, and then look inward through the gap, with a planet 120,000 kilometers across, serving as a lens hood. That is why the resulting picture looks the way it does. Saturn is backlit, its rings glowing where the sunlight comes through them from behind, and everything in the frame is being seen in eclipse. The person who arranged it was Caroline Porco. 30 years earlier, she had been a young scientist proposing, without success, that Voyager be turned around. 23 years earlier, she had sat down with Candy Hansen and worked out the shutter times for the sequence that finally did it. By 2013, she was leading the imaging team on Cassini, which meant that for the first time in her career, the decision to point a camera back at the Earth was simply hers to make. She did not make it quietly either. The date was published, the time was published, and people were asked to go outside at that moment, find Saturn in the sky if they could, and look up. It had never happened before. In the whole history of photography, from the camera bolted into a captured rocket, through the Apollo frames, through the 60 exposures Voyager made in the dark, nobody had ever been told in advance that their portrait was about to be taken from beside another world. And nothing anybody did that evening registered in the slightest. At 1.5 billion kilometers, the whole planet occupies a few pixels. There was no possibility of a wave being visible, or a face, or a city, or a continent. The invitation was not to be seen. It was to know for a quarter of an hour that the picture was being taken, which is a different thing, and is the only version of the experience available to you or to anybody else who is not one of the 24. Cassini worked for a little over 4 hours and produced 323 images. The final assembled mosaic uses 141 of the wide-angle frames, and it took until the 12th of November to be released. In it, Saturn fills the view and the rings run right across, and off to one side, well outside them, there is a small bright point that is where all of this happened, where the rockets were built, and the cameras, and the arguments about whether to use them, and where you are now. On the same day, at the other end of the solar system, the spacecraft Messenger photographed the Earth and the Moon from orbit around Mercury. Two machines at two planets on opposite sides of the Sun, both looking back at the same object within hours of each other. It had taken a little over 60 years from the first photograph of a falling rocket to reach that. Nothing, though, has gone further than 1990. 3 spacecraft in history have ever been in a position to attempt the shot Voyager 1 took. Voyager 1 itself, its twin, and New Horizons, which crossed Pluto in 2015 and is still travelling outward. Only one of them ever did it. Cassini's photograph was taken from about a quarter of Voyager's distance. 36 years on, with better cameras, better processing, and better spacecraft than anything available in 1977, no camera has ever been further from home at the moment it turned around. It could not be repeated now, even if the equipment still worked. Light thins by the square of distance, and Voyager has kept going. By the time it had reached 3 times its 1990 distance, this planet had faded to roughly 1/10 of the brightness it had in those 3 exposures. The spacecraft is considerably further out than that today. The subject is still there, and it is still throwing back 30% of everything the Sun gives it. But from where the camera is now, there would not be enough of it left to find. The picture exists because it was taken in the only decade, from the only position, by the only instrument, at the only moment when all of it was briefly possible at once. And the machine that took it has not photographed anything in 36 years. It is still working. What it has been doing instead is measuring the edge of the Sun, not the surface. The edge. The Sun is not a ball of light sitting in empty space. It is continuously throwing off a thin wind of charged particles in every direction at something like 400 kilometers a second. And that wind blows outward until it meets the gas drifting between the stars and can push no further. What it hollows out along the way is a bubble. Everything we ordinarily call the solar system, including the ground under your feet, sits inside it. The bubble has a boundary, and the boundary has structure. Coming outward, the first thing encountered is the place where the wind, still blowing but now pressing against something, drops abruptly from supersonic to subsonic and piles up behind itself. Voyager 1 crossed that on the 16th of December 2004 at 94 times the Earth's distance from the Sun. 8 years further on the 25th of August 2012, at 121 times that distance, it went through the outer wall. The solar wind simply stopped. What lay beyond it was the medium between the stars, and Voyager 1 became the first object made by anybody on this planet to leave the Sun's atmosphere altogether and be somewhere else. It took over a year to be certain of that, and the reason is a good one, because the instrument involved works in an unusual way. The plasma wave subsystem does not measure the surrounding gas directly. What it listens for is ringing. When a burst of energetic electrons comes past, flung out by some event on the Sun and travelling far faster than the wind itself, it sets the local electrons oscillating, and the pitch of that oscillation depends on how tightly packed they are. Thin plasma rings low, dense plasma rings high, and the gas between the stars is dozens of times denser than the outer reaches of the Sun's bubble. But it only rings when the Sun happens to shout. The instrument had to wait for something loud enough to set the surrounding space vibrating and then listen to the note that came back. It heard it through October and November of 2012, heard it again across April and May of 2013, and the announcement was made that September. By 2017, a different problem had arrived. Voyager holds its dish pointed at Earth by firing small thrusters in brief pulses, and the set it had been using since launch was wearing out. Each pulse achieving slightly less than the one before, so that more were needed, so that the wear accelerated. There was a second set aboard, 4 thrusters meant for course corrections, last used on the 8th of November 1980, on the way past Saturn. On the 28th of November 2017, the command went out to fire them. Nobody had touched those thrusters in 37 years, and their propellant lines had been cold for most of that time. After the command executed, the team waited 19 hours and 35 minutes for the answer to reach a dish in California, and the answer was that all 4 had delivered 10 millisecond pulses precisely as instructed. Switching to them bought the mission another 2 or 3 years. Everything now is decided by the power. The generators aboard convert the heat of decaying plutonium into electricity, and they made 470 watts at launch. They make somewhere around 230 today. The plutonium itself is still more than half present since it decays slowly. But the devices that turn its heat into current have been wearing out alongside it, and between the two the supply falls by roughly 4 watts every year, without pause and with no possibility whatever of repair. A good deal of what remains goes on staying warm. The fuel lines have to be held above the temperature at which hydrazine freezes, because if the thrusters seize, the dish drifts off Earth, and the conversation is over. Whatever is left after that runs the computers, the radio, and however many instruments can still be afforded. Voyager 1 launched carrying 10 of them. 2 are still switched on. The cosmic ray detector was turned off on the 25th of February, 2025. The instrument measuring low-energy charged particles went dark on the 17th of April 2026. What continues to run is a magnetometer and the plasma wave subsystem, the one that listens for ringing, and every one of those shutdowns was permanent, decided by people who understood exactly what was being surrendered and had no better option available. On present arithmetic, the power gives out somewhere around 2036, which means you will almost certainly outlive it. Before then, though, there is a date worth putting in the diary. On the 18th of November 2026, Voyager 1 reaches a distance of about 25.9 billion kilometers from the Earth. That number is not arbitrary. It is exactly how far light travels in 24 hours, and crossing it makes Voyager the first object built by human beings ever to sit a full light day from the place that built it. A command you send it on that day arrives tomorrow. A question asked is answered the day after. And the fastest thing our species has ever launched will have spent 49 years covering a distance that light crosses between one breakfast and the next. Beyond that, it simply keeps going at 17 kilometers a second, quick enough to reach the moon from here in about 6 hours and nowhere near quick enough to matter. In roughly 40,000 years, it makes its closest approach to another star, a small red one catalogued as Gliese 445, and it will pass about 1.5 light years away from it. That is not close. It is something like 600 times further than everything Voyager has covered since 1977, and it stands as a fair measure of how empty this galaxy actually is. The spacecraft is not really going there either. Gliese 445 is coming here, closing at about 120 kilometers a second, 7 times faster than Voyager is traveling at all. By the time the two are nearest, that star will be roughly 3.5 light years from the Sun, which is nearer than any star stands today. The encounter is almost entirely the star's doing. Voyager merely happens to be in the way. So the remainder reads like this. About 10 more years of speaking, then silence, then 40,000 years to the only star it will ever come near, and after that a very long time indeed with nothing at all scheduled. And the place it came from, the one it turned around to photograph, is a great deal smaller than almost anybody assumes. Everything that has ever been alive on this planet has lived inside a layer about 20 kilometers thick. The planet's radius is 6,371 kilometers. Divide one figure into the other, and the habitable shell comes to a little under a third of 1% of the distance from the surface to the center. Scale that down onto an apple 8 centimeters across, an ordinary one, the sort you would put in a bag, and the equivalent layer works out at around 13 hundredths of a millimeter. The skin of a real apple, measured, runs between 1 and 2/10 of a millimeter. The comparison is not a figure of speech, it is arithmetic, and it lands almost exactly. That 20 kilometers is generous too, in the sense that most of it is very thinly occupied. Going downward, microbial life has been recovered from around 10 kilometers beneath the continental surface, living inside rock in complete darkness, at temperatures and pressures that would kill anything with a nervous system in seconds. Beneath the oceans, it reaches further down into the crust to something like 21 kilometers below the sea surface. The deepest water anywhere, the floor of the Mariana Trench, is about 11 kilometers down, and there are things alive at the bottom of it. Going upward, the numbers fall away much faster. Bacteria are found in genuine abundance to about 6 kilometers of altitude, and spores have been collected from a great deal higher than that, although how much of that population is living rather than simply in transit is an open question. Between those two limits is everything, every forest and every ocean, every city, every animal that has ever drawn breath, the whole of agriculture and the whole of the fossil record, all of it inside a band which, on an apple, would be the skin. Set that against what the camera was able to see. At 6 billion kilometers, a single picture element on Voyager's narrow-angle camera covered a patch of space roughly 55,000 kilometers wide. The Earth is 12,742 kilometers across. So the smallest detail that instrument was physically capable of separating out from where it was standing was a region more than 4 times wider than the entire planet. Everything inside a region that size, every ocean, every continent, the atmosphere, the biosphere, all of the water, collapses into one number, and the number is the brightness of a single point. There is a second quantity worth having, and it has nothing to do with geology. The Population Reference Bureau maintains a running estimate of how many members of our species have ever been born. Their most recent calculation, updated in 2022, puts it at somewhere near 117 billion people, spread across roughly 200,000 years. They are careful about the figure, and anyone repeating it should be equally careful. It is the output of a model. It shifts when the assumptions shift, and it is an estimate rather than a count. About 8 billion of us are alive at the moment, which makes the living something in the region of 7% of everyone who has ever been. The other 93% are in the ground, or in the sea, or dispersed past any recovering, and every one of them lived and died inside the same 20 kilometers. You have spent your entire life inside it. So has everybody else, without exception, for the whole 200,000 years. 117 billion lives then. All of them inside a layer the thickness of apple skin on an object occupying 12 hundredths of one picture element, in a photograph taken by a camera that had 34 minutes left to run. None of it shows, and the layer itself is not a permanent feature of the planet either. It has a beginning behind it, and it has an end in front of it, and somebody has already worked out roughly when. The sun is getting brighter, and it always has been. This is not a fault in it. It is what a star of this kind does across its working life. Hydrogen fuses into helium in the core. Helium is the heavier of the two, so the core slowly contracts and heats, and the reactions run fractionally faster than they did the day before. The effect is undetectable on any human scale and unstoppable on every other. When this planet formed, the sun was giving out about 70% of the light it gives us this afternoon. That trend has a consequence. and the consequence has a date on it. In something like 1100 million years, the Sun will be roughly 10% brighter than it is now, and at that point, the Earth is no longer comfortably inside the range of distances where liquid water is stable on a surface. 10% does not sound like very much. What makes it decisive is that the process feeds itself. Warmer air holds more water vapor, and water vapor is a greenhouse gas, a powerful one. More of it in the atmosphere traps more heat, which warms the surface, which puts more water vapor into the air. Once that loop has enough energy behind it, there is nothing available to stop it. The oceans do not boil in any dramatic sense. They migrate upward, out of the basins, and into the sky over a very long time, and then they leave altogether. Water vapor that reaches the top of the atmosphere is broken apart by ultraviolet light from the sun, split into hydrogen and oxygen. Hydrogen is the lightest thing there is, light enough to escape the planet's gravity entirely, and once it has gone, it does not return. The oxygen stays behind and binds into rock. The water is not relocated, it is subtracted. Estimates put the end of surface water somewhere between 1 and 1.5 billion years from now. The famous ending arrives a great deal later than that. In roughly 5 billion years, the Sun exhausts the hydrogen in its core, swells enormously and becomes a red giant. And what happens to the Earth at that point is genuinely unsettled. The Sun will be shedding mass as it goes, which loosens its hold and lets the planets drift outward. So this world may be swallowed or may simply be scorched and left where it is. Nobody can say. It hardly matters though, and this is the part worth carrying. By the time the Sun becomes a red giant, the Earth will have been a dry rock for 4,000 million years, which means the photograph is of a temporary color. That pale blue comes from two mechanisms, and both of them are on a clock. Short wavelengths scattering through a deep atmosphere, and a great quantity of open water swallowing the red end of the spectrum and handing back the blue. Remove the oceans and both mechanisms change. The reflectivity shifts, the atmosphere becomes something else, and whatever this planet is throwing back into space a billion years from now, it will not be that particular shade, and there will be nobody in any position to remark on it. Voyager 1 photographed a phase. There is one other thing aboard that spacecraft, and it has not come up until now. Bolted to the side of Voyager 1 and to its twin is a gramophone record, 12 inches across, copper, plated in gold, sealed in an aluminium case with instructions etched into the cover explaining how to play it, including a diagram of the stylus and a chart giving the position of the Sun against a set of pulsars so that whoever finds it can work out both where it came from and roughly when it was sent. On it are 115 photographs encoded as analog signals. Greetings in 55 languages, 12 minutes of the sounds of this planet, surf, wind, thunder, birdsong, whale song, a heartbeat, a kiss. 90 minutes of music running from Bach through Javanese gamelan to Chuck Berry playing Johnny B. Good. And one track that is not a recording of anything anyone could hear. Anne Druyan, the creative director of the project, proposed that they record a person's brain activity and compress it into sound, on the reasoning that any civilization capable of intercepting the spacecraft and decoding the disk might also be capable of reading a mind from its electrical trace. She volunteered. She lay in a hospital with electrodes on her scalp while the recording ran, thinking, among other things, about being in love. That hour is on the record, and the record is engineered to stay playable for 1 billion years. Set that number beside the other one. The oceans have somewhere in the region of 1100 million years remaining. The record is rated for 1,000 million. Both are estimates, produced by entirely separate disciplines using entirely separate methods, and neither deserves to be treated as a prediction so much as an order of magnitude. But they are the same order of magnitude. which is to say that Voyager 1 will still be carrying a 12-minute recording of surf and whale song at approximately the moment when there is no longer any water on this planet for either of them to occur in. The photograph has already outlasted a good deal. It outlasted the argument, which ran for 8 years and is now a footnote. It outlasted the instrument by an enormous margin, those cameras having been switched off 34 minutes after the exposure and cold ever since. It outlasted the man who asked for it, who died on the 20th of December 1996, 6 years after standing up in a room in Washington and giving it a name. And inside about a decade, it will outlast the spacecraft, which runs out of power somewhere near 2036 and then continues traveling in silence, carrying a record it can no longer play, on a heading it can no longer adjust. The light itself has not stopped either, not the fraction that ended up on the tape, the rest of it. Everything that left this planet on the evening of the 13th of February 1990 and missed the camera, which was very nearly all of it. That light did not pause when Voyager caught its share. It carried on outward at 300,000 kilometers a second and has never slowed by any amount at all because light does not slow down. It passed the nearest star in 1994. It is about 36 light years out tonight, in every direction at once, a thin, expanding shell of one particular evening, spreading and dimming, and never quite arriving anywhere, carrying an image of a half-lit planet with a great deal of cloud over the Pacific. Consider what that photograph is, judged by any standard anybody would actually apply to a photograph. It has no resolvable detail whatsoever. The subject occupies 12 hundredths of one picture element, in a frame where the finest thing the instrument could distinguish was 4 times wider than the planet itself. The color is a translation assembled from 3 filters, not one of which was red. There is a manufacturing defect running diagonally across the whole image, put there by sunlight rattling around inside a lens assembly, and the subject happens to be sitting inside that defect by pure chance. It is grainy. It was taken by a camera that had been frozen for 9 years and had half an hour of working life left. By every technical measure available, it is a bad photograph, and it is the one we kept. What it records is not the Earth. There is not enough of the Earth in it to record. What it records is the distance, the plain fact that somebody stood 6 billion kilometers out and turned around, and that from there, this is the whole of what there is to see. That was always going to be the only information in it. Everyone involved understood that in advance, which is precisely why the request was refused 6 times, and why the refusals were right, and why the eventual yes had nothing to do with anybody being persuaded. The picture is not a discovery. It is a record of an appetite. 9 years of one man asking for something with no scientific value. 2 women calculating exposures for a target that would not resolve. An administrator deciding it was worth the hazard, and a machine spending the last of itself on an image that would tell nobody anything they did not already know. All of that happened inside the dot. The photograph does not show us. It is made of us. It is quiet out there now. The cameras have been dark for 36 years. The tape has nothing left to hold. 2 instruments are still awake, listening for the note the space between stars makes when something disturbs it, and reporting back across a full day of distance to 3 dishes on 3 continents. Wherever you are on it, the planet is turning underneath you at more than 1,000 kilometers an hour, and it cannot be felt, and it has not stopped once. The light that made that photograph left from somewhere near where you are now. Some of it came off water, some of it came off cloud. A very small share went into a telescope 6 billion kilometers away and became the only picture of this place ever taken from far enough out to be worth the trouble of taking. The rest of it is 36 light years away tonight and still moving. It will keep going after the argument is forgotten, after the spacecraft falls silent, after the oceans have gone and the color with them, and there is nobody left here to be photographed. None of which needs anything from anybody this evening. The picture is taken. It came out badly and it does not matter. More people have looked at it than have ever looked at any other photograph of this planet, and more will, long after everyone in it has finished. Rest now. Let the light go on ahead of you. It has a very long way to travel and no reason at all to hurry. And neither tonight do you. Good night.